This is the first of our training modules that will discuss the subject of conductivity as it relates to lighting fixtures. Conductivity, what do we really mean when we talk about conductivity? Well, conductivity, the two definitions we're looking at is the degree to which a specified material conducts electricity and the rate at which heat passes through a specified material. When we consider the degree to which a specified material conducts electricity, that's normally the term people think of when we think of conductivity. And that all relates to the element that's being considered. If we take a look at what would be called a conductor, piece of copper wire, aluminum wire, any kind of wire that we normally would think of as carrying electricity, the element or the feature to it that allows it to carry electricity is that the element that's part of the makeup of the wire has free electrons in its makeup, in its atomic structure, so that these electrons are the thing that flow along the wire. If indeed there are no free electrons, then we don't have a conductor. What we have instead is an insulator. Now, those free electrons can flow in any direction that they need to according to the circuitry that's applied to them or the potential that's applied to them. They go either way along the wire, it doesn't really matter. That's what's called a conductor. And there are some physical constraints that impact the activity of conduction when it comes to electricity. When we look at the physical makeup of a conductor, if we double its length, we also double its resistance to the flow of electricity. Or if we take a conductor and cut its cross-section in half, we again double its resistance to electricity, because the physical characteristics of the conductor, apart from the material, have everything to do with how much electricity it can flow through it. So the question becomes, what type of material do we really want to use for electrical conduction? When we take a look at the most conductive elements out there on the atomic chart, the top 5 conduction elements or conductors are silver, copper, gold, aluminum, beryllium. Of course, nobody goes down to the store and buys beryllium. We're familiar with silver, copper, gold, and aluminum, and obviously silver and gold are rare metals that can become very expensive in their application. And so copper and aluminum, fortunately, are at the top of the list of elements that are conductors. And these are the two that we're going to consider here when it comes to conductivity, electrical conductivity. Now, copper obviously is one that we see in most instances, and the reason for this is takes place in a couple of instances. First, copper has 3 times the tensile strength of aluminum. It's a much tougher material when you're pulling it end to end, easy to pull through conduit, doesn't want to break. It is heavier, so that comes into play later on, but also its greater conductivity allows smaller cross-section of the conductor, so we can use a lighter gauge or a smaller gauge of copper wire in order to carry a specified amount of current through it versus what we would have to do with aluminum. Also, copper is far more corrosion resistant than is aluminum. Copper has been used in roofing for centuries and lasts for centuries as a roofing material because it doesn't really corrode. What it does is it forms a little patina surface to it, and that patina isn't really subtracting from the copper, it's adding to it. And so as a result, you don't have the deterioration that you would have with aluminum. Another factor that plays in copper's favor as a conductor of electricity is that it is less prone to loosening due to coefficients of expansion. And this becomes important when you, for instance, take a piece of wire and wrap it around a terminal, a little screw terminal, and tighten it down. If we're dealing with aluminum, it's possible, because of the coefficient of expansion of aluminum, that the expansion and contraction there can work itself loose from the connection point. It doesn't happen with copper because it has a very low coefficient of expansion, and it's another reason why it's a preferred material when it comes to wiring and electrical circuits. Aluminum, in its raw state, without any additives to it, has only 61% the conductivity of copper, but it's also only 1/3 the weight of copper. And so, though it's less conductive when you compare the same copper size wire to the same aluminum size wire, aluminum is much lighter. And so even if I went with a cross section twice the size of copper, it would still be less weight than would be the copper. And as a result, we see aluminum wire used in a lot of high power transmission lines because you can run great distances because it is much lighter, still carry the electricity that's necessary without tremendous losses because you can increase the conductor size. And in this way, the weight of the aluminum plays in its favor as a conductor in this particular type of application. Now, normally, aluminum that we use or that we work with, particularly in lighting fixtures, is not raw aluminum. Raw aluminum is too soft, it galls too easy, or like when you go to machine it breaks, it doesn't just sand smoothly or machine smoothly. And so there's always additives to it, which is what creates aluminum alloys. Now, alloys of aluminum, which include mixtures with silicone or magnesium or zinc, cause aluminum to be less conductive. And so typically aluminum alloys are only about 56% or about half the conductivity of copper, which is another reason why, as far as electrical purposes are concerned, it tends to be used a little bit less as far as wiring is concerned in and day out applications than does copper. Although aluminum is much less expensive than copper, perhaps as much as a third or a quarter of the cost of copper when we get right down to it. The other element of conductivity that comes into play is the rate at which heat passes through a specified material. Thermal conductivity is very important, and in this area we begin to see a movement in the direction of aluminum as a more favorable material. And here's the reason why. First of all, if we take a look at this chart showing the properties of copper and aluminum, go down to the third item there, the one that says thermal conductivity. Now don't worry about what that W over mk means. It's a measurement of the rate at which heat transfers in a particular type of element. And you can see that copper is substantially higher than aluminum at its thermal conductivity. Now that plays in both materials' favors in different ways that we'll talk about in a moment. But day in and day out, you see this type of thing take place because of everyday cookware that you see in your kitchen. You have either copper-clad or aluminum-clad cookware. Most people have one or the other. And the reason for this is that in its raw state of stainless steel, if you were to just do stainless steel cookware, the only part of the pan that would heat up would be right in the very center. It wouldn't spread out to the edges of the pan or the pot that you're cooking in. And so the entire bottom of the stainless steel material is then clad with aluminum or copper in order to get the heat to radiate all the way to the edges and get good even cooking along the bottom. And if you were to compare copper and aluminum cookware, you'd find that aluminum clad cookware usually has a thicker cladding of aluminum on it because, again, since aluminum isn't quite as conductive as copper, then you need more of it in order to move the heat at an equal rate in order to get even cooking. Now, there's another type of cookware we see a lot of today where the aluminum is sandwiched in between two layers of stainless steel, and this is for cooking with what's called induction cooking, induction ovens or induction hot plates. This is where there isn't really a flame and it's not a coil, electrical coil that heats up, but through the process of induction, electrical induction, the pan itself actually heats up. And in order for that to happen, it has to have a ferrous material there that the inductor is reacting with, and that's where the stainless steel comes into play. But sandwiched in between the layers of stainless steel is a layer of aluminum so that it spreads the heat evenly to the sides of the material. Even within one particular element, such as aluminum, depending upon the alloy, we find varying rates of heat conductivity. Now, the material that's circled here in these various aluminum die casting alloys is an A356. Now, first of all, whether you're casting with sand or you're casting with metal, as in permanent mold would be, or die casting under high pressure, as a high pressure tool would be, it's all a form of die casting. The real difference is one is under low pressure where aluminum is poured into the mold, gravity fed, and the other is high pressure, such as what we typically think of as die casting, where it's forced under extremely high pressure into all kinds of intricate shapes. The A356 material is what classically is used in what's called sand casting and permanent molds. It's a process we use regularly at US Architectural and Sun Valley for the shapes of our lanterns and all of our fixtures. Most importantly, it's used in all of our heat sinks. And the reason why is because if you look at the bottom row there, the thermal conductivity rating of 151 versus 113 for the A360, we see that it's considerably more thermally conductive than even the A360 is. Even though both are aluminum, it has everything to do with the alloy. Now, A360, the reason that we draw the comparison to that is that if you were to take a look at most specifications, A360 is the material that most lighting fixtures are made from when they're referred to as a die-cast fixture. What we do at US Architectural is we use some die castings and some sand or permanent mold castings, some high pressure, some low pressure casting processes, but in all of our heat sinks, where the optical elements are concerned and mounting components for getting heat away from the LEDs, all of this is done using the A356 material because of its superior thermal conductivity in aluminum. And we also use, in some instances, extrusions, which are an even denser form of aluminum alloy and therefore a little bit more thermally conductive. Follow the blue arrow down to the lower right-hand corner of the chart for the 6063 extruded material, which we use a T5 tempering to harden it, and that gets you up to a 209 rating on the thermal conductivity, which is considerably higher than the 151 for the A356. You would find this 6063 material in a product of ours called the linear EXT fixture, which is has an extruded shape to it, and that again is the reason we select that material, is for its thermal conductivity. So when we get right down to it, on this realm of conductivity, whether it's electrical conductivity or thermal conductivity, what we're looking at is to select the right material for the right application. Copper and aluminum fill the bills in both of those regards. First of all, for copper, its superior electrical conductivity is perfect for use on circuit boards. Wiring traces are smaller, and you have more efficiency as far as the electrical flow on those circuit boards that have the LEDs mounted to them for the optical performance. And the superior thermal conductivity of copper means that using a small amount of copper on those circuit boards behind the LED where they mount to the board allows heat to be transferred from the LED to the general circuit board surface itself and then moved to the heat sink that the circuit board is mounted to. And that's where the aluminum comes into play. Aluminum is easily formed into complex shapes for luminaire design by extruding or casting or spinning or other such elements, particularly for castings and extrusions. And it's lightweight. It's 1/3 the weight of copper, as we said earlier, but it's also 1/3 the weight of steel. And so this means that when we look at the strength factor between aluminum and steel, we can get aluminum to be just as strong as steel if we form it properly with gussets and other support elements in there, but we don't have the penalty of the weight. We also get the benefit of having the thermal conductivity of aluminum to play with when it comes to the design of heat sinks. Its strength comes from the complexity of the shapes, but also it's the best material considering its weight and its thermal conductivity for heat-sinking components in optical systems. So that's where the two elements, copper and aluminum, come into play in the two areas of conductivity related to electrical conductivity and thermal conductivity. This is the first of our training modules in the realm of